This is a tutorial on how to use CCDLAB to do photometry on point sources. So here we have a series of images loaded, 18 images. This is just after the pipeline has been run and the orbit-wise images have been produced. So we're looking at 18 orbit-wise images. We actually have calcium fluoride and NUV silica, FUV calcium fluoride and NUV silica images here. So what we would like to do is do photometry on one channel filter combination at a time. So let's go to our FUV folder and we simply do a search for the images, and we want the most recent images. If you have it sorted by date modified, your most recent images will be the ones that show up, the ones with the longest file names and the most recent. So we'll open those. So it's 9 images, 9 FUV images in calcium fluoride. So we can scan through those. We see that the registration is performed, and let us say that this source here is the source that we are interested in. So this is a nice isolated source. There's not many other sources around it. Maybe something faint is right here. But otherwise it's what we would call a nice, clean, isolated source. So for this, we can do curve of growth photometry. So we head over here to our PSE tab, Point Source Extraction tab, and we go down to the subimage region of interest panel here, and COG stands for curve of growth. So we click on that tab and we see a circle that is now drawn around a source, and the circle is the radius of our region of interest box here. So now, to show you what's going to happen here, we click View Curve of Growth because we want to see the plot result. And let's just hit Do Curve of Growth to see our initial result here, just to see what happens. So here's our plot. Now let me explain what this plot is. This plot is a sum of all the pixels at incrementing radii, incrementing at the pixel scale. It's the sum of all the pixels within each radius. So we would start at a radius of 1 pixel and then go out to a radius of 0 pixels, and then a radius of 1 pixel, radius of 2 pixels, radius of 3 pixels, radiuses of 4, and so on to the maximum radius of the window size box here. And at each radius it sums all of the pixels within. So the result of that is that you get a count versus the number of pixels within each radius. So counts versus number of pixels. So you see that this line goes up very quickly here and then levels off to a constant slope. So why would it be a constant slope here? Of course, it is a constant slope because you are measuring the constant, relatively uniform background. Of course, if you had another really bright source adjacent, then you would see the background would not be uniform. In this case, as you sum the radii. Of course, here we have a nice clean source, and so this method is okay. If we increase the radius to include this very faint source which is out here and hit do COG, we may see that it's slightly affecting the curve here, but there are so many pixels in this sum that this faint source probably has almost no influence. It's totally suppressed because at a radius of this size, there are so many pixels within that radius, at that radius increment, that this faint source here has no effect. So just as far as getting the curve of growth that you want, there's this parameter, fit the last n points. So here we're only fitting the last 5 points, but with such a large measurement of the background, we could fit a line to more of these points to get a better estimate for the background. So if we increase this to 20, now we see that this red dot here has moved out here. That's showing how many points of the background it's fitting, and now we have a very nice fit on that background. If we increase to the maximum, it will simply stop here at the maximum number of points, and we see that the slope is now pulled down a little bit here at this end. And so of course that's not appropriate, so let's scale that back a little bit. So here, if we stop there, so that's fitting the last, so that's the last points here on this side. 44 points because what we want to fit is the background. Why do we want to fit the background slope of this curve of growth function? So we get a function y equals a plus b times x. So the slope of that curve, which is your b parameter here, the slope of that curve is your counts per pixel, because the plot of counts per pixel. So the slope is your background counts per pixel. That's what your slope is. In this case, 0.0458 counts per pixel. And of course, if you wanted that per second, then you must divide by and normalize by the reduced time keyword here, which is your exposure time. So you would do that in your spreadsheet some other place afterwards. So the nice thing about this is that your intercept, your a parameter, the intercept of this slope is the counts totally due to the source. So the intercept of this linear fit is the counts solely due to the source. It's the offset of this slope, which is being offset due to your source counts. The slope is your background counts. The intercept is the offset due to the source counts. Yeah, so the slope is the background counts. The offset, the intercept, is the counts due to your source. And so that is 4,648 counts here in this case for this image. And of course, if you wanted that per second, of course, then you normalize by the reduced time. So we probably don't need to fit that many background points. I mean, we could if we wanted, but I'll just shrink it up a little bit here so that we're avoiding this faint source out here. And we will bring this back a little bit towards the end. So that's pretty decent right there. Now, of course, there's going to be some variation depending on the radius you're using and the number of points you're using. But of course, there's variation because there's natural photon noise here of square root n. So you're going to find some variation depending on the settings. So what you do is you simply choose one that you think looks good and works good, and then you stick with that. All right, good. So this is doing a single image at a time. So what you do is you do this upon a single image, and then you can scan to a different one and look at it and see that, yes, the settings that I've chosen for the previous image are still working. And that's the idea. You choose a set of parameters which you think is working good for a given image, and then it should likewise similarly work for all of the rest of a given channel and filter. Okay. Now, you want to extract all of this photometry for all of these counts, yes? So we now click Batch and hit Do Curve of Growth, and now these are the counts for every single image. So this is the source counts for frame number or image number in the stack. So we have 9 images loaded, and so we have 9 data points here. So we see, here's a little preview here, but this data, so you see here, for example, image 8, there's the source signal, there's a background counts per pixel, and then we're told here at the end, this has all been copied to the clipboard as a table. So let's go to Excel, open a blank workbook, and we simply paste in there. So we see that we have the source signal, the background per pixel, and the image index in the stack. It's 0 based, so obviously image 0 is, or index 0 is image 1 in the stack. Now, of course, what you might like is to have the Julian date and the exposure time for this data. So we can extract that out of the header. We probably want the mean Julian date for each image. So that's the Julian date at the midpoint of the image exposure. So that's mean BGD. That's your mean barycentric Julian date for the image. So we want to copy all those, copy selected key values to clipboard. So this will copy all of these values in the stack, okay? And in the same order, 1 through 9. So copy those, key value, copy to clipboard, and that will copy all of them in the stack. So let's go over to Excel and just paste that in there. Now let's format this. This is a number, and it's a number with a lot of decimal places because it's a Julian date. So let's format this as a number, and I think there's 7 decimal points. There we are. So that's your mean barycentric Julian date, and you would also probably like the exposure time. So the exposure time is the reduced time keyword. It's also the EXP time. It's also copied. Where is this? So exposure time, same as reduce time, final science integration time. So exposure time, which is more common, or reduce time, either one are the same thing. Okay, so let's copy all those. Copy selected key values to clipboard. Go over to Excel, paste that in there. So that's in seconds. So now you can use this exposure time and divide that out or normalize that out from your source signal, and then you'll have your source counts per second at the mean BGD. And now, of course, in our case, we had FUV and NUV images, so you had to repeat that procedure for your NUV data. So we go into the filter, search for image, view as detailed list. Okay, so it's sorted by date modified. The longest file name images are the most recent, which means they're the final ones. So let's load those up. And then, of course, you'd repeat the procedure. It looks like we have a bit of an adjacent source here. In this case, it's a little bit closer. It's showing up in NUV. We didn't see it there in FUV at all. But in any case, so let's just do one at a time again. So this for the single image. You can see maybe there's a little bit of oscillation happening here. It's hard to see, but you can sort of see it raises above here and drops back down below. That's probably from this adjacent source. If we go much bigger and repeat just to see. So even though there's an adjacent source, by the time you have so many pixels, it's really being suppressed out, and your linear fit is still giving. Oh yeah, look at it jump up here actually. That's where this adjacent faint source is. So it's coming up, and then it rises up here. Yeah, so that's your adjacent source. So that tells us that we want to shrink the window and fit only this region here. So we want to shrink the window back down to not include this source. Oh yeah, by the way, if you don't have your source lined up in the center, then you'll have something that looks like this, because it's starting from the center pixel and it's summing outwards, and then it finds this main source that we actually want here, halfway out, halfway out of the radius from the center, and then it finally sums it in. And so of course that doesn't look right. So of course, to get this source in your center, the white source in the center, you double click the ROI box, the region of interest box, and that places it directly in the center. And then now we can perform that curve of growth. So this is very interesting to see. With this adjacent faint source here, we see how it rises up and it moves the offset up. So now the intercept is the main source plus this faint source, which is that small little increment there. So obviously the main source is totally dominating, but that faint source does bump the intercept up just a little bit. So now let's reduce the window size so that faint source is not included. Do curve of growth, and now we need to shrink this back a little bit. So we're probably fine right there. That's probably as good as you're going to get. Now check a few other images just to see that it's still looking okay. Yes. All right, and then now do the batch. Do curve of growth. So this is going to be scattered all over the place. If you're expecting to see a nice light curve, you're not going to, because these are raw counts. Well, you do see a light curve, but it's artificially induced because all of the exposure times are different. So really you're seeing an exposure time effect here. That's why you use Excel and the exposure time to normalize out the exposure time. Okay, so this will have now been copied to the clipboard. So we go back to Excel. So this first table was for our FUV image, and then now this is going to be for our NUV image. And again, it's going to have different mean BJDs and exposure times for your NUV images. So you would repeat this procedure of getting the correct mean barycentric Julian date for the NUV data, because obviously the NUV images are likely taken at a slightly different time. Well, here, why don't I just do it for you, do it together with you. So what do we want? Mean BJD, copy. You can actually do them at the same time, mean BJD, and if I use Control and select, then I have two selected, and do copy. And now paste. So now we have the mean BGD, and yes, you can see that they're slightly different. Well, that's actually different by half a day, almost, yeah. So the FUV and NUV image data are not always taken at the same time. All right, so it's anyway, in any case, it's good to have the mean BGD for our images, yes. And then the exposure times are, of course, different for each one as well. So, of course, you would make note of what you're doing here. That's NUV. This is your FUV, and then whatever filter it was, what was it? Was it silica? In any case, you see what I'm doing here. NUV was silica, FUV was something else. Okay, so that is the basic procedure for well-isolated point sources for extracting your photometry. There are other more complicated cases. For example, when you have two sources which are adjacent or even blending into each other, then you need to use multi-Gaussian function fitting, and perhaps I can make a video on that another time. But for now, this is how you would do photometry on a single, well-isolated point source over a series of images. And of course, if all you have is one image, then you're only doing this procedure for a single image, and you never will need to do this batch part because you only have a single image to work on. So I hope that was useful. And if you have any questions, please let me know. Bye.